Hi, thanks for joining us today. Today we're going to be talking about lesson 6-4. Particularly in this video, we will talk about how to find the area between two curves. Finding that area is crucial to lessons 6-4, 6-5, and 6-6. So please return to this video as needed in order to reach a full understanding. In chapter 5, we talked about how a definite integral produces a value assigned area, which could be positive, negative, or zero. It represents the signed area between the curve f of x and the x-axis from A to B. That area would be a positive value if the majority of it were above the x-axis. We would call the area negative if the majority of the area was below the x-axis. And we would call the area 0 if it were balanced between above and below. Equal amount of area was above and the equal amount of the area was below. However, in this lesson, and in 6-5 and in 6-4, if you are asked to find an actual area, that area will not be negative. If we're talking about the area between two curves, like this hourglass figure right here, this area is going to be a positive value. Whether it was above or below the x-axis, we would count it as positive. The way we will ensure that we are getting a positive value is to make sure we are always using positive heights. What I mean by that is the area will be made out of adding up a bunch of, this is the integral as an accumulator, which we talked about in lesson 6-1, of a bunch of heights times a bunch of widths. And if you multiply height times width, you get an area. An area of what? Well, this will be the area of a representative slice of the region. So we're going to chop up the region to infinitely thin rectangles, basically lines whose width is dx, and infinitely small change in the x direction. And the height of this line, to find the positive version of it, would be taking this y value, which is given by f of x, subtracting from it that y value, the g of x value. And that's how this is the height, and that's the width of an infinitely thin rectangle. We add up a bunch of the areas of these lines, and we would get the area of the entire region. Once more, we're doing f of x minus g of x because, as you can see visually, f of x is greater than or equal to g of x. It's much easier to remember to just use the top curve minus the bottom curve. To be clear, if this was 5 and this was 2, that would ensure we're doing 5 minus 2, not 2 minus 5, which would be what you would get if you did g of x minus f of x. If we're doing functions of y, we might want to do a right curve minus a left curve because the rightmost x value is larger than the leftmost x value. This is the same thinking for this picture, just tilted. Here we go. Find the area bounded between these shapes. Y equals x squared plus 2, a parabola. That's why I know it's x squared. It's shifted up because of the plus 2. It opens upward because it's positive x squared. The line y equals x, which looks like this. Just a nice line like that. And we're starting this region from x equals 0, and we're going to stop at x equals 1. So as you can see, my gray area is bounded by those 4 graphs. We're going to find this gray area by adding up a bunch of slices. the areas of these slices I'm going to draw. Now again, because they were functions of x, it's helpful to have a slice with a width of dx, an infinitely thin, tall, or vertical rectangle. And let's see if we can't apply the formula. So the area of that gray region will be the integral. We want the top curve, x squared plus 2. And we'll subtract from it the bottom curve. I would always recommend subtracting with parentheses to make sure that you are subtracting the entire equation of the bottom curve, not just the first term in that. And the width of those rectangles is dx. How do we get the bounds of my definite integral? Well, we would start counting these slices at the y-axis, at x equals 0. X equals 0, another way to remember it, would also be the leftmost x value. And we would stop counting these slices at x equals 1, the rightmost x value. And that's it. That's the whole area here. The height of each slice times the width of each slice. Cleaning this up a bit, just to make it clear what we're going to integrate. Something like that. There's no need to rewrite it. I'm just trying to make it clear. We're going to anti-differentiate using the reverse power rule. And we're evaluating from 0 to 1. Which, of course, you should all know by now, means we're going to start by plugging in the top bound. And then we're going to minus, plugging in the lower bound everywhere I see x. Avoiding my graphs. Just barely. Now, as you get further and further into the course, as long as you're checking carefully, mentally, that this is 0, I don't mind you writing minus 0. A lot of students typically at this point in the course, though, aren't quite ready for that. Which equals 11/6. Now, another reason not to simplify, this would get full credit on any open-ended portion. On the AP test and on my test. Whereas some people have embarrassed themselves by doing things like 8 squared equals 16. All right, next example, that's really all there is to it in the basic case. In the more interesting case, sometimes you have to find out where two curves intersect to determine boundaries for my regions. These intersections will provide you with limits of integration for your integrals. I can't emphasize enough that the idea is that intersections are the boundaries, that intersections are the limits of integration, that these words all have to be synonymous in your mind. And whenever we're finding intersections, whenever we're finding these boundaries, you must show an equation setup. Even when you're using a calculator, or I might even say especially when you're using a calculator. It's a really easy point to lose, even if you're doing everything else right, and I will grade it harshly. I will not give you any points after that. Even if you have the right answer and all of your other work is the same, if you don't show me the equation set up, I will not give you points. Let's see this in action, shall we? So, functions of y. That's another interesting tweak. Find the area of the region bounded by this thingy and this thingy. Go ahead, try to draw it. Let's see how much you remember. Did you do it? I hope you did. 3, 2, 1. The red graph you should have drawn was a parabola. It is a parabola with a y squared, which you should know means opens left or right. I hope you said right. And another point, a way you can do it, if worst comes to worst, is to think about a value you know. What's something easy to plug in? Y equals 0. Just finding the x-intercept. Oh, it would be -3. If you really struggled, you could find the x and the y-intercepts, which would be positive and negative root 3. But I also know it's a rightward opening parabola. And this is enough to get me going. 1 point and knowing it opens to the right, because we have a positive y squared, is enough. Y equals x plus 1, on the other hand, is a line. I know what it is. You can find these 2 points. That might help you out. The x and y-intercept. It's pretty good. I'll just draw it slowly. It doesn't matter. So we have that line, and we have that parabola. Again, on my test, you may be asked to shade the area between the curves, which in this case, I colored outside the lines, but I hope you see what the area between those 2 curves is. Now, this is functions of y. For a few reasons, and we'll go over this eventually in probably lesson 6.6, using these vertical slices would be bad. It would be complicated, and over here we have it intersecting itself, which is always harder to describe than you might think. Over here is not that bad, but the fact that we would have to use 2 different integrals, hint, would rule this out. So when we have functions of y, and we're just being asked to find the area, I'm going to do my best to use a horizontal slice. And this horizontal slice is thin in the y direction. It's dy. Its width is dy. So as soon as you see functions of y, or you see a dy, you have to solve for x. You need to make both functions clearly functions of y. Our parabola already is. We'd have to make our line into it. X equals y minus 1. This is crucial because that dy will mean that all of the stuff inside our integral has to have y in it. It cannot have x. So when we do right minus left, I cannot be using x plus 1. So the right side is this line. I'm saying you must use y minus 1 minus the left curve, which is y squared minus 3. This is right. The most common student mistake, in case you can't visualize it, would be something more like this. Where it has x's and y's. And as we've talked about before, never in this class will you be asked to integrate something that has x's and y's. So again, functions of y. If you notice that we have 2 functions of y, you usually will want to solve for x. A. B, that's because we're using a horizontal line whose width is given by dy. I'm erasing this. This is all wrong. That blue integral above where I'm erasing is great. Now, we still need bounds for it. This is another big difference. As opposed to my last function, I don't have clear bounds. As opposed to my last example, I can't go left to right because it's a horizontal slice. So I'm going to instead want to travel from the lowest y value in that gray region, which is there, to the highest y value in the gray region. That's another thing that dy tells you, that my bounds are going to be y values. In order to find the bounds, I'm going to be looking at intersections here. Intersections between what? Between these two functions of y. And again, you want them solved for in terms of x. We have a quadratic. Get 0 on one side. Oops, -2. Factor. You are doing this all by hand. If you want to practice for how the test is going to go. Make sure you write equals 0 right there. Y equals -1 and +2. The lowest x value, the lowest y value, the highest y value, the most negative y value, the most positive y value. And that's it. I will once more draw your attention that I'm going to simplify and distribute that negative. So many scores have been ruined from not distributing the negative. It's just sad. A lovely purple integral. You could simplify it more. That's a pretty good integral sign right there. Y minus y squared plus 2. Anti-differentiate first. Evaluate. And when we evaluate, we plug in the top bound first. 2 squared over 2 minus 2 cubed over 3 plus 2 times 2 minus with parentheses. You're going to throw away your score if you don't write that parenthesis right there. Same with these parentheses. It's really important to use parentheses when you substitute a negative value in. It means something else without these parentheses. Careful, careful, careful. There is no need to simplify this. Meaning, I'm sure it's right. That's what I get for using the mouse to make that. I'm sure this is right. If you were unsure, you felt like you did something wrong, you could simplify it, but you might just get something else wrong. Simplifying it might show you that you have a negative area, which you can't. And that would be a sign to go fix everything. So the easiest thing to do here, simplify it. Sorry, don't simplify it. Leave it like this. Get a numerical answer and stop. All right. Next. Set up integrals for the total area of the regions located between the two curves as shown. You may use a calculator. Hooray. Now, before we use the calculator, let me be clear. You should be able to tell which function is which without the calculator. Which function is my red function? Which function is my green function? We also notice that both are functions of x. They both pass the vertical line test. So we don't have to worry about solving for y or anything. Solving for x. So even if you were unsure which one's the red one, the green function is a parabola. The highest power is squared. It's opening downward because we have a negative in front. And there's only one function here that opens downward and looks like a parabola. It's that. The only other one I see is students who feel the need that it goes like this, but no polynomial has that sharp turn right there. So we're talking about this guy's the parabola, and the other one, the more wiggly one, is a cubic function. Now if you draw it like this, and we're planning on using your representative slices like that, You might notice that when we want to use our formula, top minus bottom, this guy, the red one, is the top over here, whereas green is top over here. So the top curve switches. Means we need two integrals. It could be more. If it switched more than once, we might need more than two integrals. But we will need two integrals for sure. I said integrats, which is really crazy. So we'll use a dark blue one and let's say a purple one. Because over here it's red minus green. Over here it should be green minus red. Still don't need my calculator. The most professional integral you will write will be done by avoiding writing out these two functions. Here's my idea. Don't look at that yet. Sorry. Use function names like f of x and g of x. If possible. And the reason for this is to avoid any mistakes with the negative. So I'll show you what I mean one more time in a second. For the blue integral, we have f of x minus g of x. That blue slice, top minus bottom. For the purple, we're talking about g of x minus f of x dx. Okay? Just so you can visualize what I mean by using function names. Again, one of the most common mistakes is something like this, which is basically right, except either the student forgot to distribute the negative or the student forgot that it was supposed to be minus this whole thing. Here's more like what it would look like if the student forgot to distribute the negative. Either way, those two are wrong. It's much easier to just write f of x minus g of x. And you get full credit. Oops. Sorry. Okay. Now, both of these are missing my bounds. So a bounds equation, and I really would love to see you labeling it as a bounds equation, or the intersections. Again, we're going to use names if possible. F of x equals g of x. When? Now, just clearly we're going to have three intersections. And here's where I need my calculator finally. So I'll pull that out. Now, all I've done so far is I've typed in f of x as y1, g of x as y2. Sometimes it's helpful if you label that. I'm giving you a second to catch up. 3, 2, 1. Zoom 6. And here again is where you might notice which one's supposed to be which. I just noticed that the calculator's color scheme will be different than mine. Oh well. We're going to live with it. So how do I find these intersections? You should be mastering this by now. Second, trace. 5, the intersect method. I'm going to drag that little cursor, spider guy, close to the intersection. Enter, enter, enter. And I get this value. Without doing anything else, you should store the y value. Sorry, you should store the x value, which is easily done like this. Second quit, STO for store, and we're going to pick alpha A. We're going to store it into the letter A. Now the reason we want to store it immediately is because we want to preserve the decimal accuracy here. We don't want to lose any of the actual values. Okay? So, the reason, and you don't want to store it ever into X. Let's be clear here. If I do this a little bit, if I just go left and right here, what's X now? 2.424. The calculator will overwrite X at the calculator's pleasure. So you have to preserve your decimal by storing into A or B or D or E, something like that. Let's keep finding some intersections. The main other one I need is over here. You can use the picture, which sometimes you'll be given. We know we want to get a value close to -2. That looks like where the intersection occurs. Enter, enter, enter. And I get another value. Second, quit. I want to make sure we store it. This one into B. Okay. Whoops. So we can write when X equals -2.025, 0 and positive 2.025. I left off 0. First of all, it is pretty clear. That's not a good enough reason to write it down. But I can check by hand that 0 is on both of them. I can also check with my calculator that 0 is on both of them. Trace, if I can hit it. 0, enter. 0, 0 is on this function. 0, 0 is on that function. Okay. Plugging 0 to both would give you the same exact thing. So we have those three intersections. We have those three intersections. So, those three intersections, which should go where? Well, -2.025 would be the leftmost X value in the blue region, the area where red's on top. 0 would be the rightmost X value in that region. This one would pick up where the last one left off at 0. And then the highest value in that region, the highest X value in that region, would be positive 2.025. Again, store the X values if needed for computation. It will make your computation more accurate. Just to be clear how I would type this in, we hit math 9. Now I can just type alpha B here. 0 for the top bound. Alpha trace to get this menu up. Y1 minus, messed up, minus alpha trace Y2. Using the calculator's function names to avoid any typing errors. Plus math 9. Now from 0 to A, alpha trace Y2 minus alpha trace Y1, dx also, boop-a-da-boop boop, 8.405. So storing this gives us an actual answer that's actually accurate to 3 decimals. That's the most accurate answer possible. And on a test where 4.04 would not be acceptable, you want to make sure you're getting the most accurate value possible. So that's why we're going to store X values if you actually need to compute it. So you should now be able to do all the problems your little heart desires from this chapter, this section rather. Do problems 1 through 7 on page 122. Check if you got the answers right. If you have trouble, let me know. Have fun with that. Talk to you later. Bye-bye for now.